A single perfluoroelastomer O-ring costs around 30 pounds, a completely negligible component expense for a major plant. But when it fails, the unplanned shutdown costs $40,000. And that number scales rapidly once you calculate the downtime, the compliance reporting, and the mandatory safety investigations. Engineers specify FFKM when nothing else survives. In aggressive solvents, strong amines, and high-temperature oxidizing environments, the assumption is that picking the most resistant material available guarantees a reliable seal. The material can survive exposure to over 1,800 distinct chemicals. That extreme tolerance lulls operations teams into a false sense of security. That massive financial gap between a 30-pound component and a 40,000-pound outage is exactly where poor engineering and complacency thrive. In the field, you will routinely see FFKM seals pulled from service after just 3 weeks, in applications engineered to last 3 years. The core chemistry of the elastomer rarely breaks down. Failures usually stem from specification errors, improper component storage, or poor installation. The danger starts with assuming FFKM is a uniform material. It is actually a diverse family of specialized compounds, each with distinctly different performance limits. Throwing the acronym FFKM at a harsh environment without analyzing the precise requirements of the process fluid creates an immediate operational liability. Relying on the reputation of the material, rather than matching a specific grade to a specific problem, is an expensive guess. It is not a rigorous engineering standard. To understand mechanical failure, look at chemical survival. FFKM uses near-total fluorine saturation along its polymer backbone. The carbon-fluorine bond forms a dense shield-like barrier against attack. But this shielding creates a strict mechanical trade-off, making the material stiffer and less elastic than FKM. Under sustained loads or thermal stress, this stiffness leads to compression set. The elastomer permanently flattens out, losing its ability to recover its original shape. A mechanical seal relies on the elastomer pushing back to maintain contact between rotating and stationary faces. Once compression set occurs, that sealing force drops to zero, and an immediate leak path opens. Chemical invulnerability inherently creates physical vulnerability. You cannot achieve absolute chemical resistance without sacrificing the elasticity required to maintain a seal. The first major failure mechanism comes down to the manufacturing process, specifically the choice between peroxide cures, specialized triazine systems, or bisphenol AF compounds. Each of these systems dictates entirely different material behaviors when exposed to high heat, life steam, or specific chemical agents. If you drop a steam-optimized compound into an aggressive amine solvent environment, the chemical structure degrades and the O-ring flattens out in a matter of weeks. This mismatch is completely invisible to the naked eye. The rings look identical on the shelf, and the catastrophic error only reveals itself when the critical seal completely blows out during a live operation. Specifying the correct base molecule but selecting the wrong cure system guarantees a failure. The second failure mode occurs during clean-in-place, or CIP, cycling, common in pharmaceutical and food processing. This chart shows the rapid temperature spikes and drops of a standard CIP cycle. While FFKM handles sustained heat well, rapid swings induce severe thermal fatigue. With every drop, the sealing force degrades toward the red failure zone. The third failure mechanism happens before the process starts: installation damage. Most FFKM grades have a high Shore A hardness, typically between 70 and 90. Because of that inherent stiffness, the material has zero forgiveness for sharp edges. A softer elastomer might bend around a defect. FFKM drags against it. A microscopic burr on a housing bore or a single uncleaned groove will slice into the rigid material during assembly. That microcut propagates into a full leak path within days of operation. A seal engineered to survive boiling acid will be destroyed instantly by a careless mechanic leaving a burr on a shaft. Bridging the gap between reliable operation and an expensive shutdown requires stopping the guesswork. You have to ask 3 precise questions before any purchase order is signed. Number 1, demand validation that the compound and cure system are tested against your exact medium and cycle profile. Number 2, mandate rigorous pre-installation surface inspections to prevent microcuts. Number 3, require compliance with industry standards like API 682, NORSOC M710, or USP Class 6. These standards provide the exact empirical data required to prove the material will survive the physical reality of your plant operations. There is also an undocumented quality control metric to guard against weak supply chains, checking for filler variation between batches. Compounds supplied by lower-tier manufacturers often vary in density due to inconsistent fillers. A lower-density compound directly correlates to weaker chemical resistance in aggressive media. So, when a new batch arrives, take 30 seconds to weigh the critical O-rings on a precision balance against an approved reference weight. If the incoming batch is 2 to 3% lighter than your standard, quarantine it immediately. Stop the failure at the receiving dock before it enters the plant. The time and material cost of precision specification, inspection, and measurement is negligible. The brutal reality of an unplanned plant shutdown is not. If you are relying on FFKM for chemical service and lack certainty in your compound selection or validation status, visit acumenseals.co.uk. The cost of getting it wrong is simply too high for guesswork.